delightful to be able to speak at the Haskell workshop again. Earlier this week I spoke at ICF. Do I use this? Earlier this week I spoke at ICFP, and there were about this many people, but it's a huge room, so it felt empty. Right? This feels much more, I hope, warm and welcoming. So this is just a talk, but it is written down in my blog. And we're just going to use the blog to show what I'm talking about. So basically one night I was trying to sleep. I thought back over regrets. And this was a regret about something that never got in to Haskell. And maybe at the end of this you'll think they're very good reasons it never got in to Haskell. But what I'm hoping is somebody here will think, oh, that's sort of cool. Maybe I want to do something with it. So the whole reason for doing research is so that other people can pick up on it. I'm hoping to inspire some of that here, because I'm retired now. So I'd be very happy to work with somebody. But no, I'm not going to go in and modify the Haskell compiler. So before there was Haskell, there was something called Orwell, which was sort of a dry run at Haskell, which I had done at Oxford, working with other people. And Orwell had this feature that if you, the order of the equation shouldn't matter. So if you want to write equality, right, nil equals nil is true, x cons x's equals y cons y's, if x is equal to x's and x is equal to y, else, if in any other case, equal false. So this is a wild card, of course. So if I say something you don't understand, please do ask a question. If I say something you disagree with, wait till the end to ask a question. So, and you know, it's not just for lists, right? We have two shapes, right? We would use, so this is not what Orwell looked like. Orwell looked more like Miranda and had an if and the condition at the end. But thanks to Paul Hudak, we now write our conditionals this way, so I'll show it this way. And if x is equal to y, and they're both circles, then check that the radiuses are equal. If they're both squares, check that their sides are equal, and otherwise return false. And again, you needed this else clause there. But sometimes you might not want to use an else because either one is perfectly fine, but they overlap. It's like we're defining plus of x and y, and if x is 0, then just return y. If y is 0, just return x. They could, of course, both be 0. But that will be all right, because if they're both 0, we'll return one of these two things, and they're both 0, so they're the same. But we're just asserting that implicitly. We're not checking it. So, right, well, what would it look like to check it? Well, if you'd write down this, but it would compile into something much larger. If x is 0 and y is 0, and x is equal to y, then return x. But if they're both 0 and they're not equal, something went wrong, so return an error message. Sorry, this is wrapped around because that's just the way the blog displays things, alas. And then if one is 0 and the other one is not 0, you know what to do. And if they're both not 0, then we go and do the otherwise clause. But we didn't put this in Haskell, so for two reasons. One is it's weird, right? And you don't want too much weird in a new language or people will just stay away. So we left that out and it sort of worked. People came after a while. The other reason is sometimes you do want the behavior Haskell gives you, which is just to do the equations in order. But of course, in that case, which should be pretty easy, you'd have to put an else between every equation, which just looked really ugly. So I was tossing and turning in the night, and a solution occurred to me. It wasn't a solution to any of the semantic issues, but just to the syntactic issue, because sometimes that really gets in the way. I suddenly went, oh, I could have done this. That would be nice. So the idea is right? We can do bar otherwise, but otherwise, right, otherwise in Haskell is just a variable in the standard library bound to true, right? Because it just says, okay, you've fallen through the end, just do it. What if we made otherwise into a keyword? So this is incompatible with what's in Haskell now. You need some pragma, and if you're using this pragma, it wouldn't quite fit with the other code, which is, again, annoying. It'd be nice to be backward compatible in some way. So now we would just write equality like this, with bar otherwise at the end, and the square example is very similar. And the plus example now is very similar. If you wanted to get back the old behavior, right, then you would say otherwise and follow it with a condition. That would be okay. Or in the cascading example I gave, right, we would just add otherwises before all the other conditions. Otherwise is sort of lengthy. Some people said, oh, why don't you use else or something instead? I won't get down to that level, but there might be better ways of doing it. And just to give an example that's a little bit more complicated, right, if you said something like P of x and Q of x, otherwise R of x or S of x, otherwise T of x, then we've got two groups here, and within each group we have this same behavior. So we're just breaking things into little groups. Sorry?
What's neat?
You will find out shortly. That was where I got to, and I wrote it down. I sent it off to John and Simon. This was actually not recently that I had this tossing, turning in the night and came up with this. It was 4 years ago. And I discovered the reason for writing this stuff. So Simon just didn't like it, alas, or else it would be there by now because Simon's very quick at doing things. But I discovered the reason for writing things down, which is then John Hughes can comment on them. So, write stuff down because John or somebody like John will then give you useful feedback. So in fact, John wrote back an interesting answer, and rather than me telling you, as I did in the blog, what John's interesting answer is, I will let John tell you what John's interesting answer is.
Okay, so when I saw this, it looks very nice, but there are one or two things that worried me, connected with laziness. And in particular, if you think of this translation that you've seen, in which when equations overlap, equality tests get introduced, the obvious question is, well, what if the result is an infinite list? That equality test may itself cause the function not to terminate. And so the suggestion that I made several years ago was that instead of performing an equality test, just introduce a meet operation. And what meet does is it takes two lazy values and traverses them, and as long as they are equal, it returns that part of the result. But if they become different, then it returns bottom. So you get, it's the domain theoretic meet of two values. And you have it somewhere in your blog. Right. So for integers, of course, which are an atomic type, then it's just the integer, if they are equal. So it's essentially the same as equality. Otherwise, it's undefined. But if you had a lazy list, then you would be... Okay, then nil meet nil is nil, but when you have cons, then you can independently take the meet of the heads and the tails, and thus you preserve the lazy behavior of the function. So I thought making this change would enable functions with infinite results to behave in a way more like the way they behave at the moment. Meet would need to be a class, and the compiler would need to introduce calls to meet in appropriate situations. Do you want to step back in now, or shall I go on to left-rightness?
Let's do it chronologically, so you're next.
Okay, so in that case, I would like to go down to the comment I added last night. Where does that start?
Oh, the one you had last night, just above this one.
Just above this one.
The one by Anonymous. You forgot to identify yourself.
Oh, I'm sorry about that.
There it is. Anonymous said.
Okay,
That's
can we make it bigger?
Yes. What is it? Shift, Control. Oh. Oh, Command.
Yeah, so I'm also a little bit worried about the interaction of this design with laziness and in particular pattern matching order. So if we just consider this definition here, right, that is perfectly valid Haskell today, you might ask yourselves, what is f of bottom and true? Right? And if you look at the first equation, it's clear that it should return, oh, A. Did I really say A? Oh, well, it's A. With this idea, we have to go on and try to match the other equations in the same commutative group, or the same unordered group. That means we have to match the second equation as well. And when we match using Haskell's existing left-to-right pattern matching, we have to start by matching true against bottom. And that hits the bottom, so that means that the semantics of this definition would change, right? And f of bottom and true would have to return bottom instead of A, which seems a little bit disturbing. So, of course, in this case, using right-to-left pattern matching instead would solve the problem. And so Phil was suggesting that we just let the compiler choose the appropriate order.
Not exactly. No, I said that one point, and then you came up with a counterexample that pointed out that won't work very well.
Okay. Yes.
So maybe I should show my thing, and then you should...
Yeah, go on.
So what I had in mind, right, the whole point of this is top to bottom doesn't matter unless you plopped in an otherwise. So maybe left to right versus right to left shouldn't matter as well. So what would that look like? Right, if you define, there are two ways of defining Orwell then, right? This sort of standard way, where you look at the left one first, right? So if it's false and x, you get x. If it's true and x, you get true. Or, right, we could do it the other way around, right? Look at the second argument first. And, right, so this way, if we put in a bottom after the thing that we're looking at, it's fine. But if we put in before the thing we're looking at, then of course you get bottom. And the same for this. So there's a standard algorithm for doing this, which you can find in the chapter on pattern matching in Simon's book on implementation. I saw somebody quoting that very positively the other day. I thought, oh, well, that's very nice. Except they cited you as the author. I wrote that chapter. But anyhow, there's a standard algorithm for doing this. Not clear how well it interacts with laziness. What John and I were just discussing, we thought maybe really the right thing is not to allow overlap at all, which is just what Agda does. And of course, the nice thing is if you're using Agda and Emacs and they do overlap, it gives you some feedback, which is really nice. Doing this takes you further away from just looking at the code and knowing what it does. So having some feedback would be helpful. And then John had some additional interesting ideas, which I will let him finish with, because we need to wind up quickly.
Okay. So which interesting idea were you referring to, I wonder? So one of the things that I was worried about was considering, where is it? So consider this example at the top there. Right. So here, then, there is no evident pattern matching order that one might choose. I mean, would you choose left to right or right to left? The patterns give you no clue. And this is the example which I think I don't have any good solution for.
John, maybe what we should do is for the additional stuff, let people look at the blog if they want more details, but maybe we should stop now.
Yeah, okay.
Does anybody have any questions?
Yeah, thanks. That's great. Thank you. Hello. Thank you. Great talk. I couldn't help but notice that I think the definition was called Orwell, and that was exactly Plotkin's parallel OR. And I'm sure you're aware of that.
Plotkin's parallel OR is more like the more like this one.
That one. That's the one I thought about. And it seems that the identified problem with that parallel OR is exactly what you're talking about here, that there's no canonical order or correct order, no possible order in which to evaluate the arguments. And one solution to that is Girard's stable functions, where this alternative is rejected exactly because you cannot find such a possible order. So I couldn't help but notice, it seems you're doing exactly the same thing here as with stable functions.
Yes, I think that's exactly right, and that's a really good connection to draw. Thank you.
So I think perhaps this is this may be the example that or the idea that you intended me to talk about, which is that the problem here is that left-to-right pattern matching order, or any pattern matching order, gives different semantics. So there is no sequential ordering that can implement this first definition of OR. So my proposal was that one restrict groups of equations so that all the equations in the group have the same pattern matching order. Now, in this case, since the last one matches on both arguments, that means all of them must match on both arguments. Of course, we'd want to write or true and then an underscore, but if we use a bang, as in the definition at the bottom, then we get the same strictness. So we get the same strictness in every equation, and by doing so, it then doesn't matter whether, it's a way of kind of finessing the problem.
Thank you. This one? Okay. This reminded me, this is nice, but slightly related. I would actually care about if we had OR patterns in Haskell. This looks like I thought a bit about how to get OR patterns, and a lot of stuff seems to be similar, and that how would it interact if we had OR patterns?
Well, I mean, we did an example with OR, but I don't think...
No, not OR as the logical thing, but OR can be OR pattern.
I think I know what you mean by OR patterns, right?
Okay.
Where P bar Q,
yeah.
And it says here it can match either P or match Q.
Yeah.
And that's an interesting feature, but I think that's possibly orthogonal to what we're talking about.
Okay, and doesn't make any extra complications?
I don't know whether it makes extra complications or not.
Okay.
So it seems the way this meet class works is that it will, if things don't meet, then it will fail at runtime, right? So that means your program could crash at a random point, at runtime, perhaps in production. So that seems to somewhat defeats the purpose of making it more type safe, because it's not making it more type safe, right? It just makes it crash, right?
That's true.
All right, thanks.
It means if something happens that you didn't expect, instead of just getting a random answer, either X or Y where they differ, it would crash and let you know something was wrong. So, right, some people think that's horrible, you never want it to crash. It's better if it just gives a wrong answer. But for many applications, like the ones you and I work on for I/O, that's maybe not a good idea.
So there's a certain element, the cure might be worse than the disease, right? So the disease is the order of equations matters. And so it would be nice to have the order of equations not mattering. But in exchange for making the order of equations not matter, we've got to explain something much more complicated to programmers about what the semantics of the program is and what the program means. Whereas I can be done with pattern matching. I say, equations mapped, top to bottom, left to right. Job done, 30 seconds later, everybody knows how pattern match. That is an advantage, right? There's a cost that equation order matters. So I was just pointing out there's a balance here. It's not an uncontrovertible good. And the sort of slightly unrelated point is that there's another reason why left-to-right pattern matching, specifying that rather than specifying some arbitrary order, can be helpful. It supports view patterns, in which maybe matching on one can bring into scope a variable that you use in the next, but also GADT matching. You might match on a pattern that makes a type constraint that makes the second pattern exhaustive. I'm not quite sure what happens if you try to match that in the other order. So these things interact.
So in terms of the cure might be worse than the disease, as I thought through this, I think that might be right. And that this idea of, oh, any of them might match, and if two of them match, we'll check that they're giving the same answer. Maybe that's just overkill and not the best for the, this is for the cases where you want stuff that you're pretty sure works. And maybe a much better solution is, as I mentioned, the one you find in ADDA, which says, okay, if you've got a group of things without an otherwise, then for the group of things without the otherwise, they better just not overlap. And they must be distinct. And we know how to check that. We even know how to check that with the GADT dependencies you mentioned, because So then this would just be a suggestion for the bar otherwise or something similar as a compact way of saying, here the order matters. So in ADDA, you just write them, they're supposed to go in order, but if the order matters, it tells you, it gives you feedback. Here you write it, this would be a new syntax for ADDA, say, where you can say, here I think the order matters, and the other places it doesn't. You don't need feedback. You're telling it, and if not, it gives you an error. And just for the audience as a whole, right, the way I explain all this to my students here, the fact that looking at ADDA can be quite good and give you lots of good ideas is ADDA is what Haskell wants to be when it grows up.
I think it's also important to remember that the question of whether order of equations matters and whether order of pattern matching matters, those are two separate questions. So you can perfectly well use left to right pattern matching, partly for the reasons that you bring up, and still try and make the order of equations not matter.
You brought it up, not me.
So this is not fully formed thought, that it feels to me like the equality that you want to use in these checks is like this Platonic nebulous equality that people use in equational proofs, and not the term level, 8-way to Bool equality that you get from Ego.
Well, this is for doing, right, this would sort of let you write down something quickly and then get some runtime checking. But maybe that space in the design space is less important, and spaces at the end where, run fast and break things, which is sort of what Haskell corresponds to, or do a little bit of extra work, you're less expressive, but you're more sure of what's going on, which is sort of what ADDA corresponds to. Maybe those are the two good points. And the point I talked about here isn't the best point, but still the bar otherwise syntax is useful.
Yeah, it just worries me that the like putting a user-written type class instance at such a foundational point of of the semantics of pattern matching is to me a bit fishy.
Just in regard to the person who asked about OR patterns, there's a very nice paper recently, and alas, I cannot remember the title of it, that talks about OR patterns and AND patterns in a very comprehensive way. I will put a citation to it as a comment on the blog. But one of the reviewers for this conference said, ooh, you should cite this paper, and they're right, so I will go back and add that citation.
Okay, last quick one.
Parallel OR is good because it allows us to write more terminating programs.
Yes.
And it can actually be implemented in Haskell. A variant of John Hughes's neat has actually been written up in the blog post in 2008 by Conan Elliott with his unam operator. You can race the two branches of OR, and whichever yields a value first. Yeah.
So you can imagine a compiler that inserts parallelism when it sees definitions of this sort. But note that you can't insert sparks, because the scheduler may not throw away any of these parallel executions. You really have to start Haskell threads for that. And starting Haskell threads is cheap, but it's not so cheap that you want it to be part of the implementation of pattern matching. I mean, I would guess that it is hundreds of times as expensive. Simon, does that sound plausible?
It's implementable, but it's a big step up. So I think, again, the cure is worse than the disease.
So when you write parallel function programs, the first thing you have to think about is controlling granularity, so that you only start parallel tasks very, very occasionally. And starting a thread inserted by the compiler just because you happen to write equations that overlap, no, I would not turn that flag on.
So we're slightly over time, but it's only lunchtime, so anyone who wants to get food, feel free, but we can just let Alex ask his question. I think it's fine.
It feels like implicit in this whole discussion is that we are targeting a sequential hardware where we have to choose an ordering. If we had hardware that allowed us to efficiently start evaluating things in parallel, and I'm not talking about multiple threads, but I don't know, graph reduction or something where you could evaluate both sides of the OR at the same time until one of them has returned. It feels like we're pushing a lot of the semantics of the hardware into what's going on here, and it feels like there could be something that you could target that allows some of the ideas that you're talking about here by not restricting ourselves to saying we have to do this and then this and then this and then this. Right? Is that a reasonable thing to think? I don't know what the hardware looks like.
So I think it's a priori reasonable. If we had fine-grained parallel hardware and we could just evaluate things in parallel, life would be great. That was the dream in the 80s. People have been trying to do it for a long time since then, and it has not won out. I don't think it will win out on this occasion either.
It'll happen eventually.
Okay, thanks again for our speakers, and that concludes the morning session.